I am Anil Kumar. Welcome to my series on binomial theorem. In this particular video, we'll consider all kinds of questions based on binomial coefficients. Now, this is extremely important for all the students going for higher level mathematics and competitive exams. We'll look into about 9 identities which are based on binomial coefficients, and we'll also prove them in this particular video. You can always write to me for learning from me on my email address given here, or you can contact me on the website globalmathinstitute.com. So we'll consider about 9 important questions based on binomial coefficients as given here. We'll actually have a common type of proof for these, starting with 1 plus x to the power of n actually gives you binomial coefficients with x degree in increasing order. And if we write this as x plus 1 to the power of n, you get these binomial coefficients with decreasing power of x, right? So these are the two series which help us to prove most of the identities or the results which we are going to look into in this particular video. So these are the 9 results. 7 of them I think are clearly visible, and then these are the other two. So we'll take them one by one, and I hope it is going to help all the students a lot for preparation of their examinations. So we'll begin with the very first result, which is very common, known to most people. Well, again, as I was seeing, we'll actually begin with the coefficients for 1 plus x to the power of n. So 1 plus x to the power of n can be written as n choose 0 plus n choose 1 times x, n choose 2 times x square, and so on, n choose n x to the power of n. Now, if I change the position and write it as x plus 1 to the power of n, in that case, we have decreasing powers of x, as you can clearly see. The very first identity, which is commonly used, is sum of all the coefficients, right? So we also call this as sum of coefficients. Correct? So to find the sum of coefficients, what you need to do really is in this expression, which is 1 plus x to the power of n, which gives you all the coefficients along with the x powers, you just substitute x equals to 1. As soon as you substitute x equals to 1, what you get is only the coefficients on the right hand side. And on the left hand side, we get 1 plus 1 to the power of n, and that gives you 2 to the power of n. And so clearly, the sum of all the coefficients is 2 to the power of n. Now, this is very important identity which we use so many times in proving results of such coefficients. Okay, so let's take the second example, which is now we need to prove that n choose 0 plus n choose 2 plus n choose 4 plus n choose 6. So we have even values of r is equals to 2 to the power of n minus 1, right? So last product was sum of all was 2 to the power of n. Now this time we are only considering even coefficient, right? So we are now saying sum of even coefficients. Correct? So that is what we'll prove. And for this, what we'll do is we'll again begin with 1 plus x to the power of n and 1 minus x to the power of n. Now, this time we have 1 minus. So as soon as I write 1 minus, I get alternating negative and positive signs. You see that? So when you add them up, then these alternating signs, which are negative, they cancel away. And so you get a series which is NC0. That is the first term, right? So we actually call this as the odd series, right? So it is 2 times the odd series which you get, right? So it is 2 times the odd series. Correct. So when you do that, you get 2 times the odd series, the terms, the first term, the third term, whose coefficients are n choose 0, n choose 2, n choose 4 and all. Correct. Now, on the left hand side, as you can very clearly see, what we have is 1 plus 1 to the power of n, which is 2 to the power of n. And on the right hand side, we have this series, which is we want to know the result of times 2. And clearly, the value of this series will be 2 to the power of n divided by 2, and that gives you the result 2 to the power of n minus 1. Correct? Now, here we'll have the third identity, in which case what we are doing here is n choose 1 plus 2 times n choose 2 plus 3 times n choose 3. So we are multiplying by the R value, right? So NCR sum, but we're starting with 1, not with 0. Take a note of this. So this series starts with 1, ends at n, right? Now sum of this series is n times 2 to the power of n minus 1. Now let's see how to prove it. So for this, what we do is that we the first term is missing. So we're just multiplying this by a placeholder, you can say, right? So 0 times n choose 0 we have added here as a placeholder, right? So this is kind of a placeholder which we are doing. It really doesn't change the series since the multiplying by 0 is actually 0. So it has the same series 1 times n choose 1 plus 2 times n choose 2 plus 3 times n choose 3 till n times n choose n. Now see the beauty. What we have done here is we have written it n choose n, n choose 0. We have written it in the reverse order. Or you can also write this as, now at this stage we know NCR is equals to NC n minus r also, right? So we have used this and then written these terms. Okay, so instead of NCN, we are writing NC0 and then the coefficient. So this term now is written first. So we kind of reversed the series and did this. And then add, correct? So we reversed it. So we get this series again written in a different order, n times n choose 0 plus n minus 1. So we swapped and then flipped it. Okay, now if I add these two series, what do you get? I get 2 times s is equals to, see, n plus 0 is n, correct? N minus 1 plus 1 is how much? It is also n. So for each term here, we get a coefficient which is n. So 2s equals to n, which is common, right? Times the sum of series which we need. You get the idea, right? So what we did here was we kind of uh, clubbed it as such, and what we got here is a series whose sum is known to us as 2 to the power of n, and therefore we can write this as 2s as n times 2 to the power of n, and s will be divided by 2, so n times 2 to the power of n. So is that part clear to you? So what you saw here is that the series, which was NC1 2 times NC2 3 times NC3, was rewritten in two different ways, right? And then we added them up to get a series where n was a common coefficient. And so we got our result. So this is another very important strategy to apply and solve such questions. Clear? Now let's take another one. So interesting thing here is that we had two, so NCR, R times NCR, that is common to us, right? So okay. Now let's see the other one. In this case, we have a similar series than what we had the last time. However, there's one difference. We are multiplying. We have the first term also, NC0, right? The second term is multiplied by 2, the third term multiplied by 3, correct? So what you see here is R and the multiplier is a sum is one more than, right? So multiplier is one more than R. That is what it is. So the last term will be n plus 1 times n choose n. So again, our strategy is to identify this as S, the sum of series. Let this be S. Now we are flipping again. So what we're doing it, we flip the series again, right, and use the identity, which is we know NCR is equals to N times C, N minus R. And then you get two series, add them up. So this is a brilliant strategy which can be applied to so many questions and results can be obtained. So when you do that, and now when you add, this time n plus 1 is n plus 2. So in the sum, you get n plus 2 as the common factor. Do you see that? So this time you get n plus 2 as the common factor. And inside series is 2 to the power of n. So it is 2 to the power of n times n plus 2, which is equals to 2 times s. So s will be as shown here, n plus 2 times 2 to the power of n minus 1. So that is simple, right? So what you need to do is take the series, flip the terms, and change NCR to NC, n minus r. Add the two series and get your result. That is the strategy. Okay, clear? Now let's take another one, which is this time. The question number 5 here is n choose 0 plus 3 times n choose 1 plus 5 times n choose 2 and so on. So the multipliers are odd multipliers, right? So we have odd multipliers. So odd coefficient multipliers. So that is 2n plus 1. So we're multiplying each coefficient by the odd times n, and we are expecting a result of n plus 1 times 2 to the power of n. So again, the strategy here is take your series and name it as S. So let this sum be S, right? Whatever you want to prove. Second step, NCN could be written as NC0, right? So NCN can be written as NC0. So this term, which is the last term, is written here now. So flip the series. Do you understand? And use NCR equals to NC n minus R, correct? And flip the series. Once you do that, then you add these two series, right? So the same process we are adopting for all these questions. So I hope now the process is clear. So if you have a similar question to prove, you can easily do that. So clearly, this time we get 2n plus 1 is 2n plus 2. So this sum now is 2n plus 2, which is going to be our common factor. Inside series will add up to 2 to the power of n. Now 2n plus 2 has a common factor of 2. So it could be written as 2 times n plus 1 times 2 to the power of 2. Is that clear to you? This is equals to twice the sum. So sum is divided by 2 and you get your formula. Perfect. So when there are odd multiples, that is the result which you get. Now, here is question number 6, and this is a very important result which you should remember. So we will now prove that the square of these coefficients, when you add them up, right, then what you get is 2n factorial over n factorial times n factorial, right? So basically, this could be written as 2n Cn, right? So that is what you get as your result. So that is very, very important. So sum of the squares of the coefficients is the value of the term 2n Cn. Let's see how to prove it. Now in this particular case, we'll again begin with 1 plus x to the power of n written in two different ways, right? As shown here. So these are our first two equations to start with. Now let's multiply them. So what is the product of these two equations? 1 plus x to the power of n times x plus 1 to the power of n. Both are same, right? So you get 1 plus x to the power of 2n. On the right side, I've written both the series as the product. Now, we will compare the coefficients of x to the power of n on both the sides. Now, this is a very critical step. If you know this n choose r means what? So it means n choose r. And these are the coefficients of binomial expansion, correct? Now, in this particular case, what we are going to do is, from the product, now compare the coefficients for x to the power of n on both the sides. So, what are the coefficients of x to the power of n for 1 plus x to the power of 2n? It is 2n choose n. Do you see that? So on this side we have 2n choose n. And on the other side, when you multiply these terms, what are the coefficients? So one definitely is this multiplied with the first term, right? So what you get here is, when you multiply this with the first term, you get nc0 whole square, right? This is what x to the power of n will be, right? So uh, let me just connect them like this. So that multiplied will give you the term. Let me show you this one. Okay. So nc0. Similarly, when you multiply the first and the last term, in that case you get the square of nc0 with the coefficient x to the power of n, correct? Because here we have x to the power of n, correct? And here we have 1. When you multiply, you get x to the power of n. So these are the coefficients for x to the power of n. So you are comparing the coefficients on both the sides, and then what you get is the required series, right? The required series, which is what we need, and 2n choose n as our answer, right? So this is, in a way, 2ncn. So now you have 2ncn, you can expand, simplify. So 2n factorial divided by n factorial times 2n minus 1 factorial. And when you simplify that, you get your result. Is that clear to you? So you're comparing the coefficients to prove this result. Now let's take the next one, which is we'll now see the product of coefficients. So we need to prove that n choose 0 times n choose 1 plus n choose 1 times n choose 2 plus n choose 2 times n choose 3 and so on. The last term, of course, will be n choose n minus 1 times n choose n is equal to 2n c n plus 1. Well, this can be written in two different ways. We'll just show you. So it is 2n c n plus 1, which is also equal to 2n choose n minus 1, right? So there are two ways of writing the same expression. So the question could be done for both, but the same process. Now, let us see how to do this. Again, what we are going to do is we'll begin with these two equations where the x is written in increasing order and in decreasing order. Just find the product of this. So we get 1 plus x to the power of 2n on the left side, and on the right side, that is the product. Now this time, we need to compare the coefficients for x to the power of n plus 1. When you do that, then you get this product which we are asking for. Do you see that? So these are the coefficients which you get for x to the power of n plus 1, right? So that is how. So n plus 1 is when you multiply them, when you multiply these, for example, so what do you get? You get x to the power of n. But when you multiply this with the next one, in that case, what do you get? nc0, nc1, x to the power of n plus 1. Do you see that? So when you multiply in this fashion, then you can clearly see that you get the coefficients which are n plus 1. Perfect. So that is what you need to do. So those coefficients will be 2n. So because the power is 2n, so what will be the coefficient? What will be the coefficient for the exponent to be n plus 1? Clearly it is going to be 2n c choose n plus 1. That is what the result is. So the right hand side is the required expression which we need to find, and the left hand side is the result, right? So which is 2nc n plus 1. You can expand and write this as 2n factorial over n plus 1 factorial times n minus 1 factorial. So I hope this step is absolutely clear. Now let's take the next example, which is in this case what we're doing is. So last time it was like consecutive coefficients. This time it is NC0 with NCR, right? So we skipped by number, right? R number. So NC1 and choose R plus 1. So we're skipping by R to multiply. Do you get the idea? So the concept is same. You begin with the same two series, one with increasing order of x, the other one with decreasing order of x. Product of these will give you a series which will be 1 plus x to the power of 2n. And now, what you need to do is compare some coefficients. What should they be? Coefficients for x to the power of n plus r, right? So that will give you the expression which is required. And as you know, the coefficient for this expression, 1 plus x to the power of 2n, where the x term is x to the power of n plus r, is 2n, choose n plus r. Now, on the right side, you get the expression which you need, correct? And so the result is 2n, choose n plus r, which is written there. Now, it could be also written as 2n, choose n minus r, right? Because both are same. Perfect. So remember this part, that if I have a 2n, choose n plus r, then what is 2n minus n plus r equals to? So that is equals to n minus r. Do you see that? So this is also equivalent to 2n n minus r. So the question could be either way, but the same strategy works. Perfect. The next example is very important. It says we need to now show that sum and product. So we are taking sum of n choose 0 and n choose 1 multiply by n choose 1 and choose 2. So consecutive sums are being multiplied. Do you understand? So that is what it is. So we have consecutive sums and they are being multiplied. If that is the series, in that case, what is the value of this series? Well, in this case, the value is given right there for you. N plus 1 to the power of n divided by n factorial times the whole series of n choose 1 times n choose 0 times n choose 1 up to n choose n minus 1. Correct? Let us see how to prove this. Now in this, we have a very different strategy to work with. Now what we are trying to do is we have taken a general term in between. So our general term here is n choose r minus 1 plus nr. So we are now working with a general term. So simplify a general term, which we are taking as tr, correct? So once you take this general term, which is n choose r minus 1 plus nr, let's try to simplify this. Now this is equal to n plus 1 choose r plus 1, right? So that is what it is equal to. So it could be written as in the factorial form n plus 1 factorial divided by r factorial times n plus 1 minus r factorial. Now you split n plus 1 factorial as n plus 1 times n factorial, and here the denominator you can write n plus 1 minus r times n minus r factorial. Now this could be written as a product of two expressions which are 1, the value n plus 1 divided by n plus 1 minus r, and the other one in the factorial form n factorial over r factorial times n minus r factorial. Now we have NCR as one of the factors in this, and the other factor is n plus 1 divided by n plus 1 minus r. So that is each individual factor. So we can now define our product using the pi, capital Pi notation. So it is r from 1 to n. So we have this term which is n plus 1 over n plus 1 minus r, NCR, right? So that becomes a general term. So product of all these general terms for r equals to 1 to n is what is required, correct? That is what is required. So we put them all inside, and when you expand this using the formula which we just derived here, right? So using this particular formula, we get our result that it is n plus 1, because n plus 1 gets multiplied n times. So you get the power of n, right? And inside each coefficient NCR, we get from 1 to n. So we have NC r, because it is r minus 1, right? There is n minus r inside. So we get n times n minus 1 times n minus 2 till 2 times 1, right? So they get the whole expression on the top. And now we can actually rewrite this particular formula as shown here. So we just rearrange this value, correct? We rearrange this value, and then we have written this as, so on the right side, this is the left side. Let me just rearrange this particular value, right, as here. So denominator is the n factorial, correct? So we just rearrange and wrote denominator as the n factorial. The other sums are the product of the coefficients from n choose 0 to n choose n minus 1. Is that clear to you? So that is how we are going to get our series. So with that, we end this particular video. Now, I hope with this you understand how we have solved all the 9 identities. Now, these are very important results. Some of them you may like to remember, right? And they'll actually help you in solving many examination style questions. Now, this is an exhausting list which can give you excellent background on solving similar questions. I hope it helps. Feel free to write a comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.